Hello and welcome to yet another video of Cornerstones of Math. Let me explain today's problem. Suppose that we have two-dimensional parabolic container y equals ax squared, where a is a positive real number. And we have the circle with radius r with its center located on the y-axis. And we want to lower this circle as far as it can go. That is, until the circle touches the parabolic container. This may look like a simple setting, but actually this act may end up in two different results. When the radius r is small enough, the circle can reach all the way down to the bottom of the container so that it will touch the parabola at a single point, the origin. But if the radius is big, then you can easily understand that the circle cannot go all the way down to the bottom, but it meets the parabola before it reaches the bottom. Therefore, in this case, the circle will touch the parabola at 2 points instead of 1. Our main question is this. What is the condition for radius r such that the circle can hit the bottom of the parabola, like the first case? In order to address this question in the most efficient way, let us think about this problem from a different perspective. Instead of moving the circle along the y-axis, let us just place the circle at the bottom all the time. So the circle always passes the origin 0, 0, and we change the radius of the circle to see what happens. As you can see, when the radius is small, the circle and the parabola meet only at the bottom. But when the radius is big, then the circle and the parabola have no choice but to meet at 3 different points. So with this in mind, let us actually try to calculate the coordinates of these intersection points. If the circle passes the origin, then the y-coordinate of the center must be equal to r, the radius. Therefore, we can write the equation of the circle as x squared plus y minus r squared equals r squared. If we simultaneously solve this and the equation of the parabola y equals ax squared, we can find the coordinates of the intersection points. When doing so, we must eliminate either x or y. You can solve it in either way, but in here, I am going to eliminate x and solve for y. From the equation of the parabola, we have x squared equals y over a, and if we substitute this expression into this x squared in the equation of the circle, we can eliminate x and obtain y over a plus y minus r squared equals r squared. So y over a plus y squared minus 2ry plus r squared equals r squared. So we have y squared term, y squared. And as for y term, let us write 2r minus 1 over a times y. And this equals 0. So we have y as a common factor. And we have y minus 2r minus 1 over a equals 0, which gives y equals 0 and 2r minus 1 over a. Here y equals 0 obviously means origin, and the other value means that this coordinate is 2r minus 1 over a. So we have obtained this y coordinate. And you can also obtain these x coordinates by using the equation x squared equals y over a. But this is an undesirable situation for us, since we want the circle and the parabola to meet only at the origin. That is, there must be only one intersection point, 0, 0, meaning that this other value of y must approach 0 as the radius becomes smaller and smaller. Therefore, when the radius becomes small enough, the coordinate 2r minus 1 over a becomes 0, which gives r equals 1 over 2a. The precise condition is that the radius cannot exceed this value, hence the answer is r is less than or equal to 1 over 2a. To summarize the result, if r is less than or equal to 1 over 2a, then the circle can be lowered all the way down to the bottom, meeting the parabola at its vertex, the origin. If r is greater than 1 over 2a, then the circle cannot be lowered all the way down to the bottom, and the circle meets the parabola somewhere above the origin. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.